Classical Physics Tutoring, Chapter 6, Section 4, Extension of Relativity. Okay, so we need to go back a little bit. The twins paradox. So, the twins, we have twins. One stay on the earth, another one make a trip at a very high speed, and he come back. Okay, so the speed is v. According to relativity theory, this A thinks he say the B aged 4 years on the way, and another 4 years on the way back, so 8 years. But A himself aged 15 years. Okay, but the B thinks A aged 4 years each way and 8 years, and B himself aged 15 years. Okay, so here's a problem. When B come back, A and B are on the same frame, and you cannot have a contradiction in the same frame, because when they are on a different frame, each claim, there's no way you can tell who is right. Okay, and this is apparent contradiction. They look at each other, A and B, and say, "You are younger." B said, "No, you're younger," and they are on the same frame. So this is the contradiction. It's not going to happen, and relativity theory is not addressing this. The reason is there is a turnaround time here. Okay, and turnaround time, let's see, as an acceleration, and relativity theory so far address only inertia frame, this constant speed. Acceleration is going to be the subject of the general theory of relativity. But to make the long story short, what happened is under acceleration, the time slow down. So for example, and this is not relative, the time slow down relative to A. No, time slow down on B only, because B is only one receiving acceleration. Acceleration is not relative according to Einstein, right? The A and B is moving away, or A is moving away. You cannot tell who is moving away. That's relative. But acceleration act on the B is not relative. It's not relative to A getting no acceleration. So the B's time kind of slow down dramatically, and B gain only 1 year, okay, during the acceleration, this turnaround. Okay, but because the A side clock is going, well, this guy gain another 8 years. Okay, so total 16 years. So when B come back, B thinks the A, no, sorry, this is wrong. Let's see. Correction. So A thinks the A is going to age another 5 years, so total 20 years. Okay, but the B's thinks A's clock keep going, and it's not affected by relativity. I mean the acceleration. So it's go another 12 years. So here you go. When he come back, B thinks A is aged by 20 years. And A thinks, yeah, I'm 20 years old. But you are only 8 plus whatever, make it same as 15 plus 1 is 16 years. So B thinks I'm 16 years old because clock slow down like hell during acceleration, and only 1 year, right? So during that time, the A look at the B and, hey, he suddenly gained 8 years, so 16 years. So what happened is the effect of acceleration here is going to adjust the aging back. So the A at the end is 20 years older. The B is 16 years older. So B is young. So twin paradox is actually show that when B make a trip, come back, the B is younger than A, even they were twin. The 4 years difference here, okay? And that's the effect of acceleration. Acceleration is something, and also another effect we have to consider is acceleration to the V, from 0 to V, right? And we add this effect, the accounting work out. So B, when B come back, there's no disagreement. A and B are exactly what they think. So what happened is during acceleration, clock screw up, and A gained 8 years, but B gained only 1 year during that acceleration. Okay, so it turned out to be the correct accounting. Okay, but the fact here, significant fact here is when B come back to the A's frame, the B is younger, and this is significant, right? Okay, so this causes a possibility of time traveling. And suppose you change you are in a planet and entire society travel by the huge Enterprise ship, right? And the Enterprise ship come back. The majority is younger than you. What does it mean? When B come back, B is younger, that means B come back to the future, right? That's correct. A is already aged, is future. But the scenario I gave you, entire society move and come back, they are all younger than you. That means you came to the past. So future and the past, it's possible to travel to both sides according to the relativity theory. But you cannot go back to when you started traveling, okay? Because both sides, the clock ticks. So you can go back to somewhere after you start traveling. You can never go back before you start making travel. That's why grandpa's fallacy is a fallacy. It's wrong, okay? And there are many fallacy there, and they are wrong because going back to future or past possible within the limitation that everything is within the time you start traveling. And you can never go back before you start traveling. So you cannot never go back to the time you were born because you haven't traveled yet, right? So you can easily refute the grandpa's fallacy and all other fallacy, like the Hollywood movies and stuff. Okay, but actually this is significant. Now there is an argument saying if there is a wormhole, if there is such a thing, then wormhole, what basically is this is Earth you left, then when arrive, wormhole is connected here, then without traveling you can come back, and that screw up the time too. But we don't know the details of wormhole. If it's full of acceleration inside, then we have to calculate according to that. So the basic is, even there is a wormhole, you cannot go back to the time before you start traveling. Okay, so that's understanding of acceleration is coming in the next chapter. The acceleration effect is not included in the theory of special relativity. And another thing you have to understand is non-relativistic effect. When you think about relativity theory, say this is the frame A and the frame B is moving at the V, and this cause of explosion and observation time disagree, and in the section of simultaneity I said disagreement between A and B is acceptable because it doesn't violate any physics law. Okay, because clock is ticking different time, the clock, due to the relativistic effect. But you have to consider the time the light travel to A or light travel to the B. This time, traveling time, has to be subtracted because they are not relativistic effect. It's called non-relativistic effect because they are not relativistic effect, they are non-relativistic effect. This is simply just time to travel from point A to B, is nothing to do with relativistic effect. The relativistic effect comes from the disagreement on the clock, the time. Okay, so now let's check Doppler effect, right? So the redshift, the famous redshift, the star emit the light and observer thinks this is the light spectrum is slightly shifted to the red side, means the frequency, the red side means frequency become lower slightly, and because of this the observer concluded star is moving away at the speed v, and this shift we can calculate how fast star is moving away. This is a famous Hubble scientist. Hubble figured this out, and by observing the spectrum of the star and observing the shift of the frequency, then he figured out all the stars are moving away. Almost every star has a redshift. Okay, and that's Doppler effect. And Doppler effect is different from the classical physics wave. Doppler effect equation is different because it's come from the special relativity Roland transformation equation. Okay, so for frame 1, the light seemed to travel the distance of c plus v t1. The wavelengths become this. Using this equation, we get this. So wavelengths, the change, this is the redshift. And get the pencil and paper and work it out, see how much it's going to shift. You can get actually redshift data from astronomy side and calculate, see how fast the star is moving away from the observer. When star is moving away every direction, that means universe is expanding, right? Somehow everybody is moving away from you. It's like you are a dot on the balloon, and the balloon is keep getting bigger and bigger. So the neighbor markers all move away from you. Okay, so that's kind of discussion comes in by this Doppler effect. Now, Minkowski's word, this is more mathematics. We define the time by scale ct1 and coordinate x1. So if not moving, right, then x1 is 0. Infinite speed is just keep moving without any time. Speed v is this, right? And light speed is this, and we have a limit on the light speed. So it's kind of interesting things you can observe from this kind of coordinate. The light speed is this. So any motion in this world will be in this range. And if you make a cone, 3D cone, we have 3D cone coordinate, and our world is confined here. We can never get out here because it's going to be faster than light speed. Okay, so this diagram will tell us a lot of things. And from this diagram, what we do is try to come up with Roland's transformation equation. So we define this way, and we place relativity constraint, then coordinate conversation. This is coordinate conversion. It's going to come up with, here you go, Roland's transformation. So what it is scaling factor is calculated. You can follow this the mathematics, and basically what it is the Minkowski, the derived Roland's transformation. Using constraint list. Okay, so using this, the constraint, another way to look at the constraint is this famous equation, and this constraint became very important in the next level of general theory of relativity. What it is basically this is same as Roland's transformation equation constraint. This gonna guarantee the physics law is kept the same in frame 1 and frame 2. How you guarantee the physics law are kept consistent, and this is the constraint equation. Okay, and general relativity is going to handle acceleration, but the under acceleration, frame 2 and frame 1, no acceleration and speed v is all together, is still the requirement is physics law is consistent and physics law is valid on each frame, and this become very important. Okay, so I hope you got the overview picture of relativity theory and you enjoy this video. Please subscribe.